Good morning, everyone. Today we'll be studying about backtracking, and we'll be discussing these things like basics of backtracking, identification, generalization, and then one problem we will discuss like how I can, we can apply backtracking anywhere we want, right? So, like before even like going to like watching this video, please have a clear idea of what is like recursion, right? You need to have the clear idea of recursion. Wait, let me make this a little bit small. Yeah, anyways, have clear idea about what is recursion, fine, and DP, right? Please watch the previous lectures. You should have clear idea of these things, and BT we will be discussing. So backtracking, I will be using BT as backtracking acronym, right? Okay. So now starting with basics of backtracking. So basics of backtracking. Fine. Yeah. So basics of finding that in this section we will be discussing like we will be discussing what is not backtracking. That's right, because many of you may have like came and basically many of you may have heard of backtracking, and maybe like if you are learning from someone else on YouTube only, you might have some wrong idea. If you don't, then it's fine, but yeah, let's see like what is not a backtracking. What do I mean by that? So okay, let's say that we have some recursive tree, right? Again, you need to have an idea that you need to like just for revision, let's say that we have recursion, right? We have recursion. So this it's a parent of different operations like DP, right? Backtracking and divide and conquer, which we'll be discussing later on. But yeah, so recursion is the parent of every of these methods, right? So we will be drawing. So basically, if recursion is there, you can apply DP, and in every question if BT is applied, recursion will be there, right? So if talking about uh, backtracking, there will be recursive tree, right? Because recursion is the parent. So let's uh, draw a recursive tree first, right? So let's say that this is some recursive tree, right? These are some nodes, fine. uh, let's say that you might have heard about the backtracking, that let's say we are here, right? I mean, the solution goes from here to here in this branch, and then it goes from here to here this branch, right? But if like this, right? But what if, like in backtracking, if we don't need this node, right? If we don't need this solution of the node, then we just backtrack. We just backtrack to the previous node, right? And yeah, so maybe you might have this idea that this is what backtracking is like, backtracking to the previous solution because we don't need this, right? So this is not a backtracking actually. So this particular thing, which you might have heard, this is not a backtracking. Not a backtracking. There are a lot of things in this case. I mean, there are some conditions here which we'll be discussing. So this is not a backtracking. I discussed this because you need to unlearn some things, right? To learn a new particular good way. So basically, even when we are doing the recursive calls in this thing, right? Let's say that it's recursive call and stored in a stack, right? So let's say we did n call, so fn will be called, right? Then again fn will be called, right? Even if we go here and go back, right? So this still doesn't makes any sense, right? It's still like we know, basically it does not make any sense because we are still going to that node, the stack, in the stack in recursive call stack, that will be still be called. So there's no point of it's not explicitly reverted, right? It's not, basically that's what the point is, right? You say that we revert back to the previous solution in the backtracking, but since in the recursive tree, in the recursive call, this is getting called anyways, right? So we are not explicitly reverting actually, if you see the recursive tree. So here we are not ex explicitly reverting, right? You can see that how, right? So that's the thing which I wanted to discuss, right? Now coming to more things about backtracking. So now we will really start with recursion only because this is what the parent is, right? Just for some revision purpose, right? Recursion. So recursion in recursion only we have, as I told you, we have three things, right? Which we are concerned with. One is the DP, right? One is DP. One is backtracking and one is divide and conquer, which we will be discussing later on, or maybe I will make another video in future, not with this course. Got it? So anyways, so this when we are talking about DP, right? DP, it is generally asked for optimal solutions, I mean used for optimal solutions, right? It is generally used for optimal solutions. Just for your note only, there's nothing much explicit here. Right. And in recursion, there's one more thing to note, that recursion, if question, this will be applied when? This will be applied when we have, when question, question, question deals with choices, choices plus decisions, decisions. Because whenever you see something like this, that we question deals with choices plus decisions, then only recursion can happen, right? If you have seen my previous video on recursion, you will get this point, but if you have not, please go and watch it, right, for better view, right? So recursion, basically this is what our point was in the last video as well, and that's the whole thing, that choices and plus decisions are there, then these things can be applied, right? So that was the point, right? And also one more thing that to revise only, that if let's say that in deep in uh, basically in recursion, right? In recursion, if we are having a recursive tree, right? We have recursive tree this, and then this. These are some recursive trees. At the root, at the root nodes, I mean sorry, at the leaf nodes, we will have our final answer. Got it? We will have our final answer in recursion. That's in recursion. Uh, just hold on. In recursion. I mean in basic recursion. In DP, what will happen? In DP, basically we are solving for a optimal solution, right? The most optimized and all. And in DP, we are basically what we do, like if you remember, we created a basically a matrix, right? And we these were some sub problems, right? These were some sub problems which used to get solved, like this problem is solved, then it should solve this, these two problems should solve this cell, right? Like this only, our final answer was in this, right? Final answer. Hence, even here in DP, if we draw a recursive tree like this, right? Let's say this is a main problem which is broken down in these things, right? So our final answer would be here only, right? In the root node, final answer. And in this case, root leaves, leaf nodes will have the final answer in recursion. So just a point for you all to note, just for revision purpose. Right. Now we'll see that basically coming back to DP again, right? So you can just I can just summarize whatever we discussed till now by saying this, that DP, right? DP is equal to, you can say, recursion plus some memory optimization, right? That's DP. Backtracking is actually recursion plus controlled, some control, right? It's not completely, basically it's kind of a controlled way. It happens in a particular, like our need, right? So you need to have some idea. I will explain that as well, right? In recursion DP, I discussed, right? Like just how we had this thing, right? Let me just copy paste it. So here we know that let's say we have here, this is DP case, right? This is DP. This is recursion. This is recursion. Let me write it in better. This is recursion, and this is BT, backtracking, which we will be dealing with today. So in DP, the final answer used to lie here, right? The final answer used to lie in this case, which will be a final answer. Got it? Right, because these are the sub problems which you were used to solve the final main problem, right? Now in recursion, we had our solution in the root node, leaf nodes. Why am I keep saying root? Yeah, so in leaf nodes the answer would lie, right? In recursion. In BT, what happens is that we have a path. Particularly the answer lies in a path. Let's say this this will be a path will be the answer here, right? Let me write that, like the path is the answer. Path is the answer here in this case, in backtracking, right? You'll get that point as well. So yeah, so for just for basics, right? Now next, coming to one concept, right? One concept which you should be clear with, which is pass by value and pass by reference. Uh, I I maybe explained this topic in my first or second class, I guess, but still, I will just give a quick explanation here, right? So let's say that we have two cases here. Let's say, uh, wait, yeah. So let's say that I have a main function here, right? I have my main function, and I have a string, right? String s, which is equal to ab, right? And I can run this function, like say there's one func s, I can pass that to this function, right? Now outside the main, I will define my function s, right? And this will do some operation. Let's say this does that. Wait, let me make this. Yeah. Let's say that this makes the s as cd, right? And I have this function. Yeah, that's all. Right now, uh, yeah. So now let's say that this is what happening is that is happening here. Let's say, so when I am defining a s here, right? So there is s string which has ab, right? There's one s string which has ab. Let me color it for you. Yeah. So this has ab. So this has one ab string, right? This has some string s, right? This is some string s which has ab, and it has been passed by value only. You can see that in the function it is passed by value here. So it is passed by value here, right? If you pass a particular, input as a value directly to the function, and if that function is manipulating that string, right? So what will happen is that this same string is, this same s will be converted to cd, basically. I mean, this will have one cd. There will be a new cd here, right? S string will be here, in a new address. Let's say this had some address of 10, right? 10 address. It was stored in 10 address. This will be stored, let's say, in 12. But basically we will have two things, two s, because it has been passed by value. So it will create a new, s, new string in another address, right? So this happens when you are passing by value. This happens, right? But what if you pass by reference here? Let us see that as well, right? How you can pass by reference here? Let's see. So in this case, you can see that I have passed by reference here, like using this
appresent, this appresent here, right? I've passed it by a reference here, right? So hence we can say that this string cd will, like the same string, it won't form another s, right? Basically what I'm saying is that it will manipulate, like after this function has been run, it will manipulate the same string of s only, like which was stored in 10. It will just basically manipulate that particular value only. It will not create a new string if you pass by a reference here. And in backtracking we usually pass by a reference only, right? Which will be also be clear after all, after some time, right? So you can just say that pass by value, pass by reference. You just need to have some idea before we move on, right? Pass by reference, pass by value. All right. So now coming to one more point which we can basically say, like bt. Now bt, what is bt? It, we can say that it is controlled recursion plus pass by reference, not pass by value. Again it is pass by reference, right? Reference. Yeah, so this thing you need to be aware of, right? So this is our new definition of backtracking. Like in here, this was the definition. Now we read about the pass by reference, pass by value. Now we can say pt is actually controlled recursion plus pass by reference. I'll explain how. Right, we will now be jumping to exactly the, like how it is passed by reference and controlled recursion now. So coming to first controlled recursion, right? What is a controlled recursion first of all, right? I can take an example here, right? One example for you all. Right. So let's say that I am in north. This is some north, west, east, and south. Right. So we draw this function. Right. And I am here. Let's say I am here. Fine. And my home, which where I have to go, my destination, my home is somewhere here. This is my home where I need to reach. Right. So can you tell me, like, so basically you have to go to home, but you can't go diagonally wise, right? Your way, like you can just move like in west, east, north, and south direction only. You can't go diagonally, right? So that's one constraint for you. So you have to take max of 4 steps, right? You have to take max of 4 steps to reach here, right? And discard all other steps, like as in how you will start. First of all, you basically you like if you need to reach this fast as possible, you will just start, and you can't move diagonally. You will start, you can start from here, 1 2 3 4 maybe, right? This is one way, right? One way can be, another way can be 1 2 3 4, right? You will be basically, this is how you will be approaching this, right? Another way can be 1 2 3 4, right? So these are some ways, the different colors, these are some ways you can go. But majorly, like logically, you will just move here, right? Will you go like this, like in 4 steps, or will you go like this and then come back? No, right? Can you go to like in north direction? No, because your house is here, you need to go there. Why would you go to north, east, and this direction, right? So basically you also don't need to go on east side. Yeah, you can't go to east side, you don't need to go to these sides, right? So my point is, my point is that anyways you will go in this region only, right? Because your house is here in the west, in the southwest direction, right? Your house is in southwest direction, so you will go here only in this, right? Will you won't go here. So there's no point of even considering these paths, right? There's considering these paths. So basically you won't go, you can discard uh, this whole half of consideration, right? So in recursion, like now we can basically relate as well, right? How recursion comes into play in this question. Like just this is also one question, right? Here you can apply recursion. So uh, let's say that you are let's say that you are somewhere, right? Somewhere, and you have 4 ways to go, right? You have four different ways to go exactly, right? Let's say you are here at this point, right? So you can go to any point. You can go to north, you can go to south, you can go to east, you can go to west. This is what recursion is basically, right? All the options, different options you can go, right? So my point is, okay, let me also draw this thing for your understanding only. Let's say your home is here and you are here, fine. So basically you can go like this, right? uh yeah, so you can take these ways. You can basically you will only go to direction S, W, W, right? So north and east won't be there completely, right? So can't you say that, let's say this you are at some I position and you have to take some recursive calls, right? And recursive call has these options. So can't you discard going to north and east branch? Like this will have some branch, this will have some branch, this will have some branch, this will have some branch. So instead of going to north, you will come back. Eventually you will come back because you won't find solution here because your house is not there, right? So you don't need to go to this space. This is not required, right? And so this, right? But can you do some operations to just check that if north and east are there? You don't call this whole tree. There's no point of calling this tree. Just consider this and this, right? This is what is called a control recursion. Control recursion. I mean, this is what phrase is, but yeah, this is what the point. The control recursion is basically you are you are commanding that uh, you can't go to particular recursive branch because of our conditions, right? Because south and west are the only concerns for us in this case, right? So this is what control recursion is, right? So in backtracking, control recursion comes into play, right? So that's the point which I wanted to make, right? Now, yeah. So in recursion, like as we discussed, if you have passed by value, let's say in that question a b, right? So let's say we have different nodes. Nodes represent here a string. That question s is first ab, right? S is first ab. Now if you have ab here, let's say, right? If you do some operations, it will change to CD, right? It will change to CD. Now let's say that this is one function. Let me call this is some function 1, this is some function 2, right? This function 1 2, and you have uh, ab as 0 1, right? 0 1. So you do some operation to change to basically you change to a to c. You need to change, let's say, a to c here, right? Not cd. Let's forget this. Let's say you need to change zeroth position, not a zeroth position to c, right? So you will call this function, right? And this will have what? Cb. This will have, right? 0 to c got converted. uh, cb will have, right? But again, here you can see these two are different functions completely, right? These are different functions here. These two are different functions because you know that it is passed by value. Let's say this is the case of pass by value, right? So now, but what if we pass by reference? Let's take now that example. Control C. By reference, what if the case here is passed by a reference? What we will observe here, let's see. So we have one node here, right? We have one node here, we have one node here, we don't need this node actually, but okay. We have one node here, we have one node here, right? So a b is there, right? 0 1. So you do some operations which changes 0 to c, right? And then you got what? You got cb, right? So basically again, let's say that you need to go to one. You can also change one position to c, right? So now we need to revert the change, right? If let's say we didn't need we needed cb, we needed cd, right? So let's say we didn't need this. So we need to basically revert the change, right? So you can basically call the same function again, which basically like changes 0 to a again, because we need to go to this solution. Our preferred is uh, AC, let's say, right? We need to go here. So we need to revert the change, right? So uh, instead of calling two different functions, we have the same function right here, right? If passed by reference. So you can see that like CB, you need to go back to that, right? So hence there's no two different functions. So only one value will be changed, right? So this is what backtracking actually is. Backtracking. Right, so this is what the point is, because by so you can just conclude here that point to note that backtracking can only happen if passed by reference. Right, because in pass by value you saw that there are two functions, and one was getting manipulated to making another one. But in backtracking, we don't need to do that. We need to basically discard that whole branch, right? So we can just pass by reference, and it can just basically, instead of calling another function, which will be less optimized, right? So hence you can just note that pass by reference happens, that which makes it backtracking, right? It's not just a normal revert change, right? So pass by reference happens, right? Now we will come to a new section. Now we will study about identification of backtracking, basically. How, what are the some of the identifications which tells that basically backtracking can be applied to the problem. So we will be discussing a lot of things here. So choices plus decisions should be there. If asked all combinations, then you can apply backtracking. Control recursion is there, then number of choices, size of constraint, don't be greedy. We'll be discussing all things, right? So starting with the choices and decisions, right? That is, I guess, you now know the point, that if, like, basically, to have the backtracking, you need to have the recursion, right? Because recursion, again, recursion is the parent, is the parent of BT. So BT's conditions will be equal to the recursion, and recursion has choices plus decisions, right? And I told you that like questions like, so in this section we'll just discussing like identification factors and questions which would require backtracking. So let's say that there's a really popular question of rat and maze problem, right? This rat and this maze, let's say there is a rat here, it has to go to this maze. So uh, in what ways, basically, like, just define a way that it can go to from here to here. So you can go like this or this, right? You can also go like this and this. You also have this way, right? This and this way. So you have choices and decisions, right? Choices and decisions, you need to, let's say, you need to go in shortest path, right? Shortest path. So you are making choices and decisions. So in these cases, rat maze problem, backtracking can happen. So that was the point of first point, right? Now second, so this is like a little also mark that. So this is what first indicator, right? Choice and decisions. Second indicator, what is the second indicator? It is the all combinations. So there's also one note for you, right? So keywords. So you need to be careful about the keywords here. Keywords to identify in backtracking, obviously. So first will be, if asked like all paths, if all paths have been asked, or let's say all valid Sudoku, that's that problem. Sudoku paths. If there's one question which we will be seeing later on about the Sudoku thing, right? So all valid Sudoku paths, if that is asked, right? So in general, if all solutions, like these keywords are there, right? Which means that all solutions, you have to find all solutions here. So this means that you can basically apply backtracking here, right? So all solutions, which means backtracking. Again, that optimal thing was for TP, right? Optimal solutions. But if ask all solutions, all possible paths, then PT can be applied, right? That was the point. Simple. Now coming to third point, right? Third point is what controlled recursion, which I told you that again, let's say there's one search space, right? And you know that this and this won't be useful. You just need to search here and here. So basically, you like in your tree, you will be discarding like let's say one, two, three, four, right? So you just need to deal with one and four, right? So one, four, and you'll be discarding these two, but you will be considering these spaces. So it's kind of like controlled recursion, right? So that was the third indication. If that is being asked, if question is like framed in this way that you just need to consider a few space, right? If you are drawing, if that your home, you have to go to home northwest, sorry, southwest. That question, then BT can be applied, right? That is one point. Now coming to second, which is number of choices. Number of choices, right? So in recursion, if you recall, in recursion, they were basically, if we were making a recursive tree, there were only two nodes, right? Only two nodes coming out. So number of choices, but in BT, number of choices are many, and by many I mean many, actually, right? And sometimes it is even variable, like in our case north, west, south. We knew we knew that there are only four possible ways that the guy can go: north, south, west, east, right? So there were different choices, right? Like these are choices, but in some cases it can be in some cases it is variable as well, right? So like if these cases are there, then there's a slight thing that BT can be applied, right? So it should be like the large and variable if the size of the, and sometimes it is also the case that the number of choices is also sometimes equal to the number of, let's say we are given some uh, string, right? And you need to do some operations and all. The size of string, it is also sometimes equal to size of string, right? So you can just keep a note of it, right? So these are some indicators. And now coming to fourth one, which is actually really important, and it's very very important, right? It is size of constraints, right? So let's say that we are given size of constraint, like in even in lead code questions you may find the size of constraints thing. Like let's say like it is something written like this, right? The size of constraints, right? Where n is the basically string, and I mean n is some number, right? So if these are the cases, if like there's an exponential, if the size of constraint are exponential, like, and if the time complexity is also 2 of n, or n of d, or n factorial, right? And where n is basically a whole number, right? So yeah, right. So that if that's the case, then BT can be applied. So if 10 is to 3 to 4, it's like this size constraint is in this way, then most probably BT will be applied. So please also keep a note of the size of constraint in the question. Please don't ignore it. It is also a good factor of deciding if that will be applied or not. Right. Now last point would be, don't be greedy. Don't be greedy. Like all combinations, like you basically need to define, you need to judge here that what you need to judge. All combinations, right? Or single best answer. This is what you need to judge in this way, right? So yeah, so you can say that DP, in case of DP, it is applied where basically It's applied because where optimal is asked, right? So optimal solutions is asked, right? And it is kind of like even greedy solutions, even greedy method where optimal is asked, right? So let's also discuss this with one example question, right? There's one question here. I guess after this you'll get good idea. So question is the about the largest number in K swaps, and this is actually really popular as well. So you might have also heard of this question. So let's say that you are given some numbers, right? One, two, three, four, five, six, seven, right? You're given some number, and you are also given a variable k is equal to 4, right? And you need to make largest number, right? So k is basically the number of swaps. You need to make the largest number of given these numbers using 4 swaps, right? So let's say that k is equal to 1, like of at one swap. What you can do here, you can basically very logical. Basically, if you see, if you basically need to make 1 2 3 4 5 6 7, you need to make the largest number of first swap. What you can do, you can just basically see what's the largest number here, 7, and you can just replace it to the first position. So it can be 7 2 3 4 5 6. So this is what, sorry, 1 6 and 1. So this is what the point is. I'll be writing here now, right? So after k, like after one swap, your new number would be 7 2 3 4 5 6 1, right? And now let's say another swap. What you can do, you can just make, you can just bring the 6 back to here, and 2, you can just swap 6 and 2, right? So if you do another swap, what will be the value? 7 6 3 4 5, this will be 2 and 1, right? Yeah, makes sense. Now again k is equal to 3, 7 6, again swap. So 7, wait, I did some mistake here. This will be 5. Yeah, 7 6 5 5 4 3 2 1, right? This will be the case, and the final would be what? 7 6 5 4 7 6, wait, 7 6 3 5 3 4. Oh wait, 7 6. What I'm doing? 7 6 5 4 3 2 1. This will be the this case. Yeah. Okay. Let's just, okay. This will be the basically this will be the last k is equal to 4 swap. This will be our answer basically that. Yeah. So this will be our thing. But now, as you said, as you can say that this is a greedy approach actually, right? This is a greedy approach here. This is a greedy because you basically you had a multiple number of swaps possible swaps, number of swaps you can do, right, to get the best solution, right? So this kind of like greedy way, it's like you are being greedy to basically, you are doing a lot of effort to make the best solution. You are being greedy, you are being more greedy, right? So that's the point. So it is, so greedy, you can say it is a long term uh, work is done. When the long term work is done, then greedy comes to the play, right? That's the point. So let's say, also let me write this here. Let's say we need to make the largest number in one swap only, right? In one swap only. But this, yeah, but this does not happen, right? Let's say you need to make the largest swap with one number, like, sorry, largest number with one swap, right? But this won't happen because this won't be the largest number, like after one swap this won't be the largest number. So greedy, in a way, it's just for long term purpose. I mean, long term work is done, then it is a way. Otherwise it won't work in some solutions. Let's say I have one more example of this one. Sub example. Let's say that 4, 5, 7, 7. You need to make it in one swap only. So k is equal to 2, right? Let's say k is equal to 2, as in there's a one swap possibility, right? K is equal to 1. Okay, let me take it 1 only. Right. So basically, okay, let's take it 2, minimum number, right? So let's say what you can do here is that at k is equal to 1, after one swap, what you can do, you can just bring 7 here, right, in the at the first position, not the second. So 7, 5, 7, 4, 7, 5, 7, 4, right? You can do this either, yeah, or you can just do k is equal to 2. You can just bring here and here, or you can just again another swap. If you're doing, you can just bring this to here, right? 7, this will both become 7, 5, 7, right? This is what one solution is. But another solution in the duplicates happen. Let's say we have 4, 5, 7, 7. But in this case, like, we are doing it in some other way. K is equal to 1, k is equal to 2. Let's say we swap these two instead of the last one. What will happen here? 7, 5, 4, 7. Now again, if I do again swap after k is equal to 2, I will get 7, 7, 4, 5. Now can you see the difference in this and this? In the duplication, this occurs generally like 757, 745. So it's always better to go in this way, because here we will have a bigger number, right? So that was in the duplication, this happens generally. So when duplication is there, greedy won't work here, right? So when duplication is there, greedy won't work sometimes, right? Because you can just see here, right? What if the greedy approach took this way, right? What if the greedy approach took this way? It can happen anytime, right? So there's a thing here. So hence you can say that here, if the duplication is there, right? If the duplication is there, then greedy won't work. Then backtracking can help, right? Then in this case, backtracking can help, right? And one side note for you all, BT is actually just a recursion, right? Let me write. Like, you will now later on, you will basically, you will we will be doing question first in recursion, right? But you'll feel after recursion that it's more complex, right? It's more complex, hence you can apply PT. Basically, what I'm saying here is that when we are doing those questions, we will start with PT. Sorry, recursion. Then you will feel that it's more complex, and that will make you think. Well, I mean, basically, what I want to give is that I want to make you all feel that recursion is getting more complex, and if it is getting more complex and the question is satisfying all the identification things which we discussed, 5 points, then you can apply BT here, right? So that was the point, right? And this feeling you will get by practice only, right? I can just give you some pointers, but the main thing is practice, right? Now we will come with generalization generalization of backtracking, right? So let me mark this. Now we will see the generalization, right? So let's say we have uh, we have BT, basically, which is actually like recursion is the parent, right? I'm writing this again, right? So basically recursion is the parent, right? And you can also say that the backtracking will have all the traits of recursion, right? That's logical, right? And uh, Also now drawing the basic flow of first recursion, right? So what was the recursion? Recursion was simple. Let's say we have one function calling its own function, right? That was the function, but that was the recursion, but used to be stopped by using something called as base condition, right? Base condition were used to basically stop the function to call itself after some condition is required, right? So now we will start writing the basic flow for now. So starting with writing the code, right? Just a basic. So let's say that we have some void func, right, which takes some parameters which we don't know right now, right? Yeah. So let's say if there's one base condition which is getting satisfied, then stop the execution, right? Stop the execution. Enter. Yeah. And else you can maybe, okay, let's say that we have some vector int we have some vector int. It's just a I'm not, just don't focus on the syntax. I'm just writing this has some value. All right, this has some value. And yeah, and in main function, basically in main function, I'm defining, I'm passing v here, right? So now, right now, it is passed by value, right? It is passed by value. So to make it pass by reference, what I can do is I can just add the and, right? So this will become pass by reference. Again, I'm writing generalized pattern. I'm writing generalized code for PT. Yeah, so that is the whole point of doing all this. I'm just writing a generalized code for PT as we go. Like first, for now we just know that it is pass by reference, right? So I'm just passing it as and b, right? This will make it pass by value, right? So also one side note, uh, also before that, let me also move to some things, right? So let's say that we have one void solve which also takes some parameters, right? So if I can also write the whole thing, I can also write if is solved, right? If this is solved, basically if this is true, if this is true, right, then maybe save or print the answer, right? This is what we do basically, right? Print, save or print the answer, and then you basically stop, right? That's the void solve thing. And one note before we go to, basically this what says that if the solution is solved, then don't do that. It's kind of like base condition only, right? It's just like these are just same things, right? But one side note for you, right? One side note, right? Please have a note of this. These are the tips which very few people will come tell you, like bt, like in bt we'll be using this solve function a lot, solve function, right? But please note that in big organizations, like in big companies, right? If you crack the interview, go to big company, you have the job, right? So always use appropriate appropriate function names which tells what it's doing. Like in DSA generally, this is actually a really good tip. Even in my current where I'm doing my internship, right? They are heavily focusing on writing the good and quality code, right? So it is really important for writing good quality code, right? This is, hold on. So things like this will make your code, will improve your code quality basically, right? In the big organizations. But in, like, currently, and I doing the DSA and all, no one will see your code, right? You will just run it into the compiler, the result will matter there, right? But I would say that still follow, just write a relevant type of function name so that you have the habit of writing good quality code, right? So that's just some side note.
Right. So second point which we covered was like it is basically the BT in BT. In BT, there are number of choices. Number of choices are large. Number of choices are really large, right? So let's say that this we have recursive tree. It will have a lot of different choices. Right, there are different choices we will have, right? And number of it can also be a variables. The number of it can also be variables. Just like that was this what we discussed in BT. This happens generally, right? So uh, also like in recursion, let's say not recursion in general, I'm asking if you have one function, right? If you need to call it again one function, again function, let's say uh, 10 times you need to call this, 10 times you need to call this, how can you improve this? You don't need to write that again. It's just a basic logical thing, right? You can just apply a for loop 0 which goes to I is less than 10, I plus plus. Basically you can just apply this loop and that will do the operation, right? So yeah, this one point you need to take care of. And since we have different types of choices, we need to go to every node, right? Every things. The point where we'll have the controlled recursion that we don't need to go here, that will come afterwards. But first for now, starting the code, we need to go to every possibility, every possible code, choice, right? These are the choices actually. Choices. Choi- Choices, right? So again I can just modify my code, right? So I can just add like here, let's say we have this, right? Yeah, let's say we have this function and we need to basically call that, again and again. What I can do is that it's really easy. I can just, you know uh, yeah, so I can just like apply for C in choices, right? For C in all choices, basically. I'm just writing the code, not the. Please don't focus on the syntax. This is not the Python, but yeah, like just solve. I can just write like, let's say that we have this function, right? I can this solves a particular thing. I need to go to all the possible uh, nodes. This is solved, so this will basically C, this will be C1, this will be C2, C3, C4. So C1 first, it will go to C1, then it will check to C2, C3, so on. So we will be writing this in our code, in our final code, right? So that's that. Next point, hopefully the next point we can see that as well. Next point will be the control recursion. Now as I told you, in control recursion, what happens in control recursion, basically. In control recursion, let's say we have again this north, south, west, east, right? This is north, south, east, west, and our home is where? Here. So we don't need to go here, here, and here. So let's say that we have some recursive tree, right? This, right? I have north, south, east, and west, right? So what I don't need to go to north and east, right? So I don't need to go to north and east. I can just have my concentration right here, right? So what I can do to make this, what changes I can do in this code, to make this, right? Very easy, very easy. I can have, let's say, I can just write that if choice is equal to s or slash w, just then apply that for loop and then do all that operation which you want to. Basically I can have that check, right? Or maybe instead of like I need to write the general code, right? So what I can do here, I can have one if is valid. Basically if it's valid is true, then do the for operation and whatever you want to do in that recursion call. this is valid. This is valid is basically this condition. It will be depend on uh, question to question. Yeah. So that was the whole point of it. Right. Now writing a proper general first our first general code. Right. So first general generic code. Right. So yeah, so let's say we have a function of void solve, right, which has some parameters. I'm not writing that right now, right, and I can have this is solved is equal to true if it is already solved, right. Then you can just save or print the answer. It is this was the base case. Again, why base case is followed here? Because it's a type of recursion, and let me note it. So in this question, this is the base condition. Why this is base condition? Due to recursion being a parent. So we need all that, right? Again, it will make sense because you're calling the function inside, so you need to stop it, right? So that was the case. Now for controlled recursion, what we can do is that for C in all choices, again we need to go to first. Okay, so like now I will be writing the controlled recursion code, control Z, right? So wait. Yeah, so for control recursion. First, I need to first go to all these choices, right? Then after that, I will control that recursion. I need to first go to all these choices. That's why I'm writing this code first. Then we will have the check, right? So for C in all choices, right? Here uh, you can have if basically is valid, which means that whatever condition we have in our question, if is valid is true, then only you perform the function, basically not for loop, not has to be for loop always. You perform the function, and then yeah, just do all that thing you basically the question demands. So this is what our first generic code would be in this one, right? uh, Yeah, so this is our first generic code. Now as we go we will keep adding this cases and questions, I mean sorry, code in this generic pattern which we are finding right now, right? So now next concept which we learned was the pass by reference. Right, now how we can apply the pass by reference here. Why we needed to pass by reference? Very again I will revise it, that we what if like we need to go back to here, right? But if we do the pass by value, that won't mean much anything. We can make the a percent, and we need to use pass by reference in BT, which we also saw, right? So what changes I can do here now, right? Let me, can I copy and paste that? Yeah, let me copy and paste that one. It will be easy for both of, for everyone, for me as well. Yeah, so let's say we have this function, right? Generic code we have. So we make this, do this. Yeah. So we have this void solves if solve is equal to true. Yeah, and in here in this function void solve, I can make it to accept variable and write uh, a percent variable, right? I can make that, right? And for C in these choices, for C in all choices, that is fine. If valid is true, and then function in this function we can pass. We will basically what will happen here, right? Let us also examine if this is called again in this function basically changes in variable. So before passing this right here, wait, so here, like calling this before passing it here, uh, so before directly passing to here, we need to make some changes in the variable, right? So changes in variable. We need to make some changes in variable, right? Before passing it directly. Uh, I can explain that in one case that so okay, let's say that here, uh, yeah. So this will call basically a variable variable. Right. So first we got into the for C. We got into the for loop which has C in all choices. So let's start from C1. Right. C1 is passed. So let's say if we have some function C1, it will add with the variable. It will add with that variable. Right. Then let's say after basically if this loop is end, this like if C1 is operated, then we will go to C2. Right. So after C2, C2 after C2 is passed, so our function will have C1 plus C2 plus variable, but we don't need to consider this. We don't need C1 again, right? We don't need C1 again. Why? Like because we just need to check for C2, right? This will depend on question to question, but yeah, C2, let's say C2 variable, right? So hence we need to basically revert here, right? Exactly here only we need to revert. So I can say we need to revert the change to this avoid this behavior basically, right? Because C1 will come in between of the next operation, which we usually do. Hence what we can basically write is that we can make V plus C1, right, plus or minus C1, right, plus C2. We can do that. This will in the next iteration will give us V plus C2. Yeah, so we need to make this change. Hence we need to make this will result into this. We need to make this change so that we get C2 plus variable, right? Or let me just use the proper syntax between lines variable. Fine. So we need to make this changes to basically revert back to the our case, which we need to consider, right? So what we can here basically we can modify this. We can for now I'm just writing. We can just modify this like first we will do the change like before passing we will change in var, and then we will be passing a percent of v, right, calling the passing at v, and then we will revert the changes of v so that this does not happen, this error does not happen, right? So that's the point of this, right? Now we can now conclude. We can also say that what bt is equal to basically controlled recursion, right? Plus pass by reference, pass by reference, and plus what, large number of choices. If large number of choices are there, then mostly we can apply beat backtracking. So this is one good uh, point to note basically, right? So yeah, so that's the point till now we are considering this. So now we can basically, this is what the conclusion is. Now we can, this is what the whole final template is. We can do one question, or we can start doing one question, which is basically I will be doing permutation of string. It might, you can do it in your own recursive way or all. But I will do, first I will show the recursive way, and then you will realize why it is like too much complex, and you can use backtracking to make it more efficient. Fine, that is the point of this, right? So first we will do the recursive. So let's, right, so recursion we will apply. We will make a recursive tree, and then we will see that there will be two cases right here, right? two cases we can say. One choice will be we will have many choices, many choices, and second will be the controlled recursion. We can make it controlled recursion basically, right? So also you can also say that string s. Let's say that we have string s, which a b c, and we are not considering the case of duplicates for now, just to make it simple, right? So this is the input. This is the input which we are given, right? Input. This is the input which we are given right now, right? And output would be what? So what will be the output first? Also, let's understand the question as well, right? Output will be all the permutations, basically a permutation of the string given, right? So output would be ABC or ACB, right? Like in this way, BAC, CAB, and CBA. Right? This is all. We are not considering the empty spaces as well, right? So these are all the permutations, right? This will be the output, output, right? So all unique possibilities. Again, in the question, it is asked all unique possibilities. All unique possibilities is asked. First of all, you can just figure out, like, for now, first of we are doing recursion for like firstly, then you'll go to backtracking. But even without seeing going in that way, in your question you can see all unique, right? All possibilities. So you can just get that hint using the identifications we discussed, like all possible paths, all possible things, right? So backtracking can happen. That's first indicator for you. But for now, we'll be doing recursion first because this is the first question, right? So now you can also say one more indicator of recursion or backtracking, that we need to basically fill these three spaces, and in each space we have the we have three choices basically, either to put A, either to put B, or to C. Same for this and this. So we have we have choices, right? We have choices, and we need to take decisions which automatically equals what? First, recursion is like a basic tool for you for optimizing our more solutions. So please, again I'm saying, please go watch and watch the recursion video, and then you can watch this again, right? So in recursion video we discuss the IPOP method as well, right? Output input method, by making this method. We used this method to make the recursive tree, right? So let's make recursive tree now, right? Recursive tree. So if you don't know about the input output method, then uh, you need to go watch the recursion video, right? So yeah, so let's make the recursive tree basically. It's very easy. This will be good, also a good um, revision for you, right? So IPOP method, using IPOP method. So in IPOP method, I have one IP, I have one OP, right? IPOP method. We have input as A, B, C, and for now output is empty because we need to start making the tree, right? So yeah. So now I have three choices. I have one, I have two, or I have three. Yeah. In each choice I have, either I can put A, I can put B, or I can put C, right? So now again following this pattern only. So if I chose A, right? So IP, OP, IP. Let me also write that IP, OP, IP. So if I chose A to write that, what will be the input? I am choosing from A, so input will have BC only, right? And output will have A because I have picked A, right? Similarly in IP, here I am choosing B, so AC will be here, and output I have B only. C if I choose, then A B, I will have C as an output. right? Now again, recursive tree requires us to make two more choices now, because in IP is not empty till yet, so we have two more choices to make, right? Because there are two elements here, so we can make two more choices here. Similarly in all the cases, right? Let me draw that quickly for you. So as so now starting with A B C, right? B C. I can either take B, I can either take C, I can either take A or C, I can either take A or B, right? So now again, B, like if I take B, so in input I will have only C, and in output I will have what, A and B, right? So that is one choice. If I take only C from the input, so what will be left? B will be left, and I will have A and C, right? Yeah. And again, if I take A, I will have C, and in output I will have what? I will have BC. This is BC. Yeah, and then after that I will have A left in input and BC. Is it right? C B A. Oh, this will be BA. Yeah, and A B C. Yeah, right. Now in this I am taking out A. So B I will be left A C. Here I will be left with A, and I will have B C. Now again, recursive tree is not over it. Why? Because I have one input left. So this will give me, these all will give me some solutions, few solutions, which will be our ultimate answer basically. So yeah, that only. So this will, our this these are our final answers basically. So this will be A B C. This will be A C B. This will be B A C. This will be B C A. This will be A C B. This will be A B C. Sorry, B C A. Yeah. So using recursion, you can do all this, and your all the possible factors, possible combinations will be present here. But again, these are repeating, right? So you can see that ABC is a unique. Again, you need to find unique solutions. So ABC, ACB, BAC, BCA. So this BCA and ACB are repeating. So basically, these this tree is repeating. These are the repeating solutions, repeating, but we need only unique solutions in this question, right? So again, so that's one point to be, we will be addressing that later on. But again, we have a large number of inputs, right? So we can just also say that the large number of inputs might need ET. Also, we have one more thing, that this is repeating. So maybe backtracking can help that, because in backtracking, what was used to happen? Uh, like if we have that answer, we should not go to AB, because this will only create this one. So this, it will, we can discard this control recursion, we can do, right? So hence we can have the PT here. But now let's say that we have some duplications also, right? So let's discuss that as well. Unique permutation. Let's say I have A, B, and B, right? A, B, and B, and I can arrange it to A and B. Fine. Let's say, okay, I need to write that. Yeah, let me also A. Yeah. Okay. So what happened here? Let me tell you. Let's say that we have A, in zeroth, one, and second position, right? So what if I have put my A here? So this is one solution, right? But what if I have put my zeroth A here and this one here? These are same, but they are like, but they are, I mean, same. even the index is same, but yeah, they are same basically, right? They are repeating, same case, same conditions, they are repeating, right? So in these cases, what will happen? Okay, let me also draw recursive tree for you all, right? Let's say I have A, B, right? I can go, I have three ways, A and B, right? So I can choose A, so which will uh, be left, AB will be left, and I will have A here. In this case, AB, I will have A. In this case, AA, B. So can you see here? I can go A, I can go to this way, right? I have A. Yeah, it will do some operations to give me the uh, solutions, right? Two solutions to give me. If I go back here, you can see, right? Again, these are same. So can't I discard this? This will give me same repeated solutions as we saw here in this case, right? So this will give me repeated solutions. So I can discard and then go to here, right? So this is what controlled recursion is, again, controlled recursion. We can apply this controlled recursion here, right? So both will have the same recursive tree. These both both will have same answers it will give. So there's no point of doing this again, right? So that's why controlled recursion comes into play here in this case, right? So now coming back to in this case, right? How we can remove like, let's say that we got these answers. Okay, let me just copy all of them. Let's say that these are the our solutions which we got after recursion, right? So these are the solutions where this and this are repeating, right? So what are the ways which we can basically at the leaf node, these were at the leaf nodes, right? These are the solutions. How, what we can do to remove the duplicates, right? We can just, so one way, there are many ways to do that. We can basically one way is that we can just use the normal recursion, like use recursion normally, and then basically uh, what remove duplicates by iterating by iteration basically just make a hash, make a vector, and just put the unique elements here like one, two, this, and then you won't, because the vector will already contain that, right? But there's a drawback again, right? Because we are ultimately doing the we are ultimately doing that recursion, right? So this won't be this won't be useful, time will be same, time will be same, because we are running that tree as well, right? We are running that tree again, right? So time will be same, so there's no point of doing this. So second way, there's a second way. What can be the second way? How we can remove it? We can just basically we can let's say that we have AAB, right? We can make it as AB. We can remove the duplicates, remove from IP, remove from input only. That can be done. That, and this, in this case, there will be only two solutions, because A and B, right? So this will be a best way, right? Another way can be controlled recursion, which we will be following. So last way would be the controlled recursion, which we did, right? We can use you can use this question, control recursion, to just have the output as these, and not call this recursive tree, right? Not call this recursive tree at all. So third, control recursion won't call that value, right? So we can do that, right? First, writing the now comes the coding part, right? Now we can just write the code part, recursive tree, right? So it's the last final code part. So first we will be approaching with recursive curve, right? So I want to create a string, basically vector string. I need to create want to create a string. It basically like the, let's say I have permutation, find permute string s. I am giving one string s, and I need to return a vector string, a vector of strings which have all the combinations, right? That's why I'm doing this. Now I can have another string, right? Another string v, another string v, and I can have another function which will basically commute the permute, let's say I can pass s and I can pass v as well, right? And v I'm passing, why? Because I'll be creating a void function, right? So this generally happens, but it's not the case of backtracking. That's why I'm passing and v. uh, I'm see, like I need to return this vector, right? And the permute function which I'll be creating, it will just be a void function. That's why I'm passing by reference, I'm not passing by value, right? So this will just give me some, basically this will just give me the answer, right? So yeah, ending this, right? Now now writing the main function, which is the, I mean, the function permute. This will have string input, right? This will have string input, and this will have string output. I can pass an empty string as well here, right? I can just pass an empty string, emp string. You can define it if you want, like string output it will have, and then it will have a vector which will be an passed by reference, right? Because it's a void function, right? So I need to edit that. So pass by reference because it's a void, right? So if ip dot size, if input size equal to 0, writing the base condition, right? v dot push back output, basically in the base condition, in this condition, when the base condition happens, like when the input is empty, in these cases the input is empty, right? This is the ip and this is the output, right? So ip empty, input is empty, so just push the basic output to the vector v which we are creating, a string which will have all that things, right? So that's what, why I'm using that pushback. This is the base condition, right? That's done. Now we'll push back. Now let's iterate to all the choices which we have. How many choices we have? ip dot size, input size, right? I plus plus, fine, is done. Now I can have two strings, basically string new ip, right? And this will have string new output. I'll tell you now the function which we will be using, basically, right? So just for your note, okay, let me explain this as well. So let's say that we have ip, we have we have output as this and this, A, B, C. So what I'm doing here is that I'm using a for loop, right? I is equal to 0, this will be I is equal to 1, this will be I is equal to 2, right? For loop ip dot size 3, so hence 3, right? And this will be, I will be have B, C, A, I will have A, C, B, right? So hence basically what I'm doing is that I need to create a new input. So this new input, how will I create this new input? This is new IP and this is new output, and this is what I'm running back to the function so that it calls again recursive tree, right? So how will I create this new IP BC from ABC to BC? How will I create that? I can use something as, basically I can just use sub substring method. I can use substring method of CPP, right? Which will have uh, one value, which can have one value as 0. It will from 0 until what we need, till with a pointer, right? We can like, see, if you need to make ABC as AB, we can have substring to till 0 1 1. So this will create basically BC, right? So the point is, that I can just create whatever, wherever my pointer is, Let's say I have A, B, C. My pointer is here, I. So I just need this part and I need this part. So that's why I can just put new string as IP. And for the new output, I can just OP plus whatever SI has. Right, this is what the logic is, and hence I will be writing that. If you still find it tough, you can search about this substring method. Right, so I can have substring method as ip dot substring 0 to I. Right, this will create 0 to I plus ip dot substring. This will create what? I plus 1, because I need to go like after one things, right? And this will have just output OP, yeah, OP plus the IP of I. I can just call that, right, IP of I, right? And hence I can just call that permute again with new IP, new OP, and what? New IP, new OP, and vector V, which is defined. So this is the recursive solution. Right? So now the the point is now that I need to basically not go to the second, third branch, right? Like let's say that I have this basically I have some choices, one, two, three, right? So I need to create a control recursion, right? So let's say that this was A, this was also A, and this is B. So I don't need to go here. Can't I just store like whatever output this gives me? Can't I just store it at some map, unordered map, I can just store it on a map, and then after iterating to here, like going to this branch, I can just check if this unordered map will have this combination or not. If this has A, if it has A, then don't even continue this. Just go to next branch, right? So this unordered map I can use as a hash table to best store the results, right? And this I can just insert that check here, right? Okay, let me do that as well for you all. Right. So I can just modify this. I need to create basically before for loop I can create one unordered map, right? Or unordered map. I can create one unordered map, right? Uh, Unordered set actually, and which will have the char. It will be named as MP, let's say. Okay? And then inside the for loop, like as you go inside the for loop, you can just have a check. You can just first insert ip dot insert. As you are iterating through this, you can just insert ip dot I, right? That's done. And then after insertion you can just also have a check, right? If mp dot find, if the map has that IP which you want to iterate, right? Then only map dot, if it is like basically if you have gone to all that, if that is happening, if the pointer has iterate to all till the end of the map, then only execute this map, right? Else just get that answer which is already there in the return, right? So this is how we will be basically using this. We'll have kind of controlled recursion. Fine, that's the whole main point. This is the final code. This is what the whole point of this is, right? So just to revise, we discussed the identification, generalization, and this permutation question, where we just found that if we are drawn this recursive tree again, recursion tree, if you can draw, then you can write any kind of code. And with recursion tree, after drawing recursion tree only, you saw how these are getting repeated, how we can basically make. So in our this code, if I want to record it with this code, so the pointer will be like, okay, A, this will give me these results, right? So in the map, in the unordered map, in the map we will have BCA, right? So basically in this until here, BCA, and what will BAC and BAC. This will have in the map BAC will be there. BAC will already be there in the map. Hence, this operation won't occur. Similarly, ABC, ABC is already here. So this will be also already be there in the map, right? Map. So this operation will already not, it won't basically execute. Hence, using map, we can have the control recursion. So this is what the whole point was. And so yeah, so homework for you all would be just revise this whole thing. I will be, maybe I will make in more videos of backtracking in future. The rat maze problem, if you can do the rat maze problem, you can go ahead, you can just start. So this will be your homework. Basically, you can just start the rat maze problem. You can, or not start, you can just try out the recursive way, and then maybe you can go ahead, right? So ending right now, we'll be doing more of these sessions. So stay tuned, subscribe, and see you in the next class. Thank you.